Hello! Today I'm going to talk about an interesting circuit I found for overvoltage protection. So I'm going to put that up on the board now. Almost gotcha. Okay, so this is the circuit. It is a Zener diode and two PNP transistors here. So if you're unfamiliar with them, I'll give a quick explanation as I'm going through the circuit. So as I said, this is for overvoltage protection. So let's say this is your load. Let's say it can't really exceed 5 volts. There's a little bit of tolerance, but you absolutely can't go past 6 volts. So that's the note. We know that we want to cut off any voltage here that's greater than 6 volts. So the way I'm going to start that is by looking at this Zener diode first. So this Zener diode, what it is it's a diode that is built for a specific reverse voltage that it breaks down and lets a bunch of current through without damaging the device. So I'm going to go ahead and say this is 6 volts here on the Zener diode. At 6 volts, it will break down and let current flowing through. So with just that in mind, I'm going to go ahead and say let's apply 5 volts to V in. So let's do circuit analysis. So we can see that there's 5 volts here, and we know that no current can actually flow through this Zener diode here. So then we can take a look, okay, well what would happen on the PNP? If you're unfamiliar, a PNP is basically a switch/amplifier, but we can model its terminals here like this. It's essentially two diodes facing in like this. Just relative to base. I'm not going to talk about from here to here. This is closed, or it allows current to flow through when it's on, and it doesn't allow any current to flow through when it's off. So back to the circuit analysis. 5 volts here, we look at here, and we see, okay, well no current can actually flow from this section up because this is also 5 volts. It's shorted to it. So no current's going to flow here. And down here we can see, okay, well this is connected to ground through a resistor. So this should be around 0 volts. But we have 5 volts here, so it's not going to let any current flow. So we see that nothing actually flows over here. And I didn't go too much into detail with the PNPs, but just know that this is essentially the terminal that controls whether it's on or off. And it's controlled based on whether there's any current flowing actually from here down to this middle section. So because there's no current flowing, this switch is off, meaning that there's nothing can flow actually through here. Okay, so then we can kind of ignore this section and go straight to the next PNP transistor. We see there's 5 volts here, and we can see, okay, there is ground here. I know nothing's flowing this way. So then we have about 0 volts. This is just pre-current flow. And we know that this can be modeled as a diode, like I just said a second ago. So it's not actually 0 volts, it's 5 volts plus this voltage drop across this diode, which is around 4.3. The diode drops 0.7 volts, something like that, and so the voltage here is 4.3. Since current's flowing, the switch is on, meaning 5 volts can move through this and go to the load over here. So when you're below this Zener conducting current and all of that, it just behaves as an open switch or a closed switch that lets it flow straight to the load. There's a whole lot of complex biasing. Actually, I won't say it's complex. You should look into it if you're interested, but there are important voltage biasing and current behaviors related to the PNP transistor. But let's go ahead and jump up to, I'm going to say 7 volts, and it's important I'll explain the importance of why I didn't just jump to 6 and I went to 7. So 7 volts. Well, we know actually that there's a reverse breakdown voltage at 7 volts because it's greater than 6. So we know that this will, with reference to ground, this terminal will be 6 volts. And it'll kind of maintain that constant voltage there. It won't the more voltage you apply up here, it won't change. This will always be 6 volts. So current is now flowing through here from 7 volts through this resistor and down. And as I said earlier, the PNP can be modeled as a diode section here. So since we have 6 volts here and 7 volts here, we can actually start to get current flowing through this PNP transistor. So current will flow from this top side through the middle and then down through this transistor. And because current is flowing, we now have this switch is closed, so current can actually flow through here. So now we have about 7 volts at this point. Because there's 7 volts, then we can see that this diode here is now reverse biased, meaning no current can actually flow, which turns this switch off, meaning this is now floating. There's no voltage here. So that ignores some of the details of it ignores some of the details of PNP behavior of like those edge boundaries, but this is the general gist of how this circuit works. So if you're interested, I'd recommend looking more into how PNPs work. I think they're uncommon, and I understand that. When I was in university, they didn't really teach it too well. But they're interesting, and you can make circuits like this. So what I'm going to do now is show this on a circuit just to show you this does work. Okay, so here's my circuit, and there's a couple things that are different, which I'll explain. So we have 5 volts up here on the positive rail, and this is the main section that's different. So you can see here, this is not actually a transistor. This is called a TLV431. It's basically a zener, but it's programmable, and it's programmable by the resistor value here and here. So just you can treat this section as a zener. I didn't have any zeners on hand, and this lets you pick a specific voltage reference that the zener would break down at, so to speak. So that's what's different. We can see here that this is the PNP, the first one in the circuit, which is connected to the base of the next one with a resistor to ground. So this is the other circuit that shorts the ground. So you can see through this transistor, I actually have my load. So that's the circuit. The resistor values, they don't particularly matter. You just it's more important for biasing the PNP transistors for the correct current. So yeah, I'm gonna glaze over those for now. So right now I have 4 volts connected, and this is biased for around 6 volts, somewhere in that ballpark. So if I turn this on, we can see that we actually do have current flowing through the load, and that's expected because it's under our voltage protection. And I can set this up now to 5 volts, and we still have current flowing. And if I go past it to 6 volts, still current flowing. It was in this ballpark. I think it's 6.3, 6.5. And if I step up one more, it turns off. And so that's that behavior we're seeing, where 7 volts can actually start flowing through this zener diode, which means that current is flowing through this first PNP, which essentially just creates a short from 7 volts to the base of the PNP that's switching on the load, which means this one won't turn on. And if I bring it back down, I can just bring it back to 6 volts and we see current again. And I'll just go ahead and see what happens if I get the exact reference. So instead of 6, I'll go by millivolts. So we have 6.1, 2, 3, 4, 5, 6, 7, 8. Okay, so around 6.8 volts, it breaks. And if I just bring it back down 1, it should turn on again. Alright, so that was the circuit, over voltage protection. I thought it was pretty interesting. Example cases, if you're using like a buck boost converter that is a bit finicky, I was using one like that recently. Having some over voltage protection is a good safeguard in case something goes wrong. Plus, there's other cases. I don't know if don't know them off the top of my head though. But yeah, so that's going to be this video. I'm still working on the Matrix project, and I have an RC car project I'm working on, which is going to have some mechanical components, which I'm not as comfortable on. So I think it'll be a fun one to work on. So yeah, that's going to be this video. Bye.